This is one more example where I will show you how to find electric fields from dipoles. Now there are some differences between the previous example and this one. So here again I have, this is the x-axis, that is the y-axis. Everything takes place on the 2D plane defined by xy. I have dipole 1 here, plus q minus q. This is the origin, O, and another dipole here. The two dipoles have the same separation, so this S is the same as that S, and then the charges are different. Here I have plus q minus q, here I have plus 2q minus 2q, where q is 1.6 10 to minus 19 coulomb, and S, the separation between the charges, is 10 to minus 3 meters. Now what I want to find is the net electric field at the location O, at the origin. That is my unknown, and since I know that I have two dipoles, I have two contributions to the net electric field at the origin. One is the electric field from dipole 1 at the observation location O, plus the electric field from dipole 2 created at the observation location O. Now I need to calculate both of these independently. The one thing that I have to pay attention now is this is dipole 1. The dipole axis for dipole 1 goes along the y direction. Okay, that's the dipole axis for dipole 1, but the observation location is here. So that means that to find the magnitude of the electric field created by dipole 1 at the observation location, I need to use the expression for perpendicular to the dipole axis. And that is 1 over 4 pi epsilon naught, my constant, times the dipole moment P divided by the distance to the power of 3. So this now will be 9 times 10 to the 9. Remember, I'll write it here. The definition of the magnitude of the dipole moment is the charge Q times the distance S. So now P, I have, this is dipole 1, I have only plus 1Q. So it will be 1.6 10 to minus 19 times S, which is 10 to the minus 3. And then divided by the distance. Let's make the distance from the center of dipole 1 to the origin, let's make it 0.50, so I'll be to the power of 3. And the result is 120, and I have 10 to the 9 minus 19, so I will be minus 10 minus 13 newtons per coulomb. Now I want to find the direction of that electric field. What I have here is just a number. I know that the positive, the charge, the plus Q, will create an electric field at O that points away, and that is not that much away, so let's make it, it's gonna be somewhere like this way, and minus Q will be pointing towards minus Q, so it's gonna be something like this. If I add those two, I'll get something that points in that direction. So this will be E from dipole 1 to the observation location. Let's erase the rest. Now I'll do the same thing. Oh no, I'm not done yet. Now that I have the number and the direction, this direction is the negative y direction. So the arrow, the vector will be E dipole from dipole 1 to the observation location is going to be 0 minus 120 times 10 to minus 13, 0 newtons per coulomb. And now I will do the same thing for dipole 2. Same idea, the observation location is perpendicular to the dipole axis for dipole 2. So the magnitude of this is, I'll use the same expression because it's also perpendicular. The magnitude of P. And now the numbers are 9 times 10 to the 9. Here I have dipole 2, and dipole 2 has 2q and minus 2q. So I will have 2 times 1.6 times 10 to minus 19. I do have the same separation as before, so this is 10 to minus 3. And let's use a distance here that is 0.3 meters, and that's to the power of 3. And this is equal to 1100 times 10. 9 minus 19 becomes minus 10 minus 3, so minus 13 newtons per coulomb. Using the same process with the one I used for dipole 1, the electric field at O from dipole 2 can be broken into the two contributions from the two charges. So at O from the positive charge is going to point away from the positive charge, and from the negative charge to O is going to point towards the negative charge, and the sum of the two will give me a net electric field that points down. So that's going to be, so this will be the electric field from dipole 2 to the observation location. And now I can move on and write that as a vector with my x, y, z components from dipole 2 to the observation location. That will be the negative y direction. So 0 minus 1100 times 10 to minus 13, 0 newtons per coulomb. And now using, let's say I'll set this to be equation 1, equation 2, and equation 3. Then the sum becomes 0 minus times 10 to minus 13, 0 newtons per coulomb. And that means the net electric field points in the negative y direction, and it's going to be an arrow that looks something like this. Okay, so this will be E net at the observation location. This is the sum of the short arrow pointing in the negative y direction and the longer arrow pointing also in the negative y direction. So this is the net electric field at O. Again, same idea. When you work on this, pay attention to where is your observation location, whether your observation location is on the dipole axis or perpendicular to the dipole axis. For both of these dipoles, the origin was perpendicular to the dipole axis, and that is why I used this expression. And then make sure that you are comfortable finding the directions at the observation, the direction of the electric field at the observation location from the dipole. If you do not remember how the electric field around the dipole looks like, simply break it down into two steps like I did for dipole 1. Find the direction of the electric field at O at the observation location from one charge, then find the direction of the electric field at the observation location from the other charge and add the two, and that will help you write the electric field vectors. And when you have all electric field vectors that you need, put them together, add them together to find the net electric field.